When we talk about statics, we're talking about something that is a part of every civil engineer, industrial engineer, mechanical engineer. You're going to go through a course of statics. It might be a set of courses in statics. Statics is the basis of Newton's first law problems, except that now we're going to apply that to both force and torque. But it's more than that. The word static here means that we are in static equilibrium. So not only is the net force and the net torque equal to zero, but our object is at rest relative to our environment. It's the basis behind all construction. You want to build something that will stay there. In Florida, we have to contend with hurricane force winds. So the strategy on building in Florida is different than the strategy building in California, where you're dealing with the possibility of earthquake. The bigger your structure, the more complicated you're going to have to deal with the forces that are acting in the building. And it's not just about the forces. When you study statics, you're also studying material science. You use statics to figure out how the forces are going to be distributed throughout your building. You use material science to figure out what materials you can use to support that building. And they go together. I know that, I got a few of you in here who want to be architects. Architects are about aesthetically pleasing. Civil engineers and industrial engineers are about making the structure and making sure the structure can pass code inspections and be something that has a durable lifespan. When we're dealing with a static problem is to be able to tell me how the forces are distributed in a system. We're going to deal with nothing but simple systems, but it involves these two things. Dealing with a net force equals zero problem and a net torque equals zero problem. So I can't emphasize enough that being in Florida, you get a chance to see some of the trade-offs that we have for some of the structures we design. Anybody who's from another state has had the advantage of seeing some subtle differences in the way other states decide to do things. For example, just look at the way our traffic lights are hung. Anybody from another state knows that traffic lights are done differently in almost every other state. And part of the reason is because it's cheaper to do the traffic lights the way other states do them. Generally, a pole on the side of the road with something that goes in front of the top of the road with the lights right there and one of those for each part of the intersection. We don't do it that way. If you look at almost all of our lights, except for those around the airport that have to be low because of the airplanes, we string our lights across the diagonal of most intersections, and they're all on cabling. The cabling is used because it allows the wind to pass through without having it disrupt the lights. You put major platforms with lights on it in front of the intersections, when the winds hit, they start to move back and forth and oscillate and generally fall out of the sky. Now, even with the high winds we had with the last hurricane, we did lose a lot of traffic lights in the town and country area. If you drove around there, like driving back from evacuation, you saw them laying in the middle of the road. They were there for weeks. But still, we generally string ours up using two major pylons on either side of the intersection with a couple of cabling systems in the middle. So that way the air can pass through and not disrupt the lights and not knock down the structures. These are decisions that are made in service to the environment in which our structures have to exist. Now, I say all that knowing that we're going to deal with some of the stupid, simple structures here. So these are going to be easy questions. But if you ever take a statics class, these two-dimensional examples that we're going to talk about, turn into three-dimensional examples almost immediately. So we're going to deal with just two-dimensional examples, and a lot of ours are going to be very simple. We're taking the meter stick, and we're going to apply a group of forces to it. The meter stick itself has its own force of weight, which is at the center. And Simon, how much is that? 0.9. There we go, 0.9 newtons. It's at the 50 centimeter mark. Now, on the left side, there's a string holding the left side. Let's call this TL, and it's at the 20 centimeter mark. There's a string on the right side. It's at the 80 centimeter mark. We'll call this TR. And we're going to add a load condition to the bridge. And the load's going to be added at the 30 centimeter mark. And it is a 500 gram mass. Take a quick minute and tell me how many that is in newtons. You guys are sharp kids. Don't use 10 here. We're trying to do this in the laboratory, so use 9.8. And I'll call on one of you in a second. So yeah, that's going to be 4.9 newtons. Now, it's not clear to you because I didn't do it, but I'm pretty confident that I can hang that mass on the meter stick and the meter stick won't go anywhere. So this particular problem satisfies the conditions for being in static equilibrium. Net force equals 0, net torque equals 0, and the velocity of the object is 0. Let's start with the net force relationship. As there are a number of forces acting, but we are tracking all of those forces, it shouldn't be too hard. One of the things I'm not going to be doing any longer is drawing a free body diagram, especially in a situation where we know the net torque is going to be involved. We could reduce all of this to a dot, but we still have all the forces clearly labeled, and we can tell what direction those forces act without having to draw a dot. You guys okay with that? We want the extension because we need the extension of the object now to deal with the placement of those forces. So we'll draw the forces on our diagram here, but understand this diagram is supposed to help us deal with where the forces are applied. That's necessary for torque, but it's not necessary for force. So it looks to me like the forces are just up or just down. They're not in any particular direction. So net force is 0. I will make upwards positive, and we get T on the left plus T on the right minus 4.9 minus 0.9 equals 0. Right? The four forces summed up and set equal to 0. You'll notice pretty clearly there's no way to solve for TL and TR unless we had some kind of symmetry that allowed us to believe they were the same value. That symmetry doesn't exist. So one equation, two unknowns. This is why we need net torque. Net torque is going to allow us to generate another relationship that also can be used to figure out the size of the two tensions. The difference here is that torque values require that we consider 3 pieces of information. I'm going to ask a question. I'm going to call one of you out here in a minute. What does R represent? I'm going to call on somebody. I'm really hoping this person can tell me the answer. Everybody understand what my question was? Corbin, can you tell me what R represents?
The distance from your object to the pivot point.
All right. I'm going to say it in the reverse. It's a distance from the pivot point to where the applied force is. So it's important that we remember that this actually comes from a cross product where R is a vector. So saying where it starts and where it points gives us the direction of that vector. So the torque arms are always from the pivot point to where the force is applied. That's not in your notes. Put it in there now so you can answer this question tomorrow when I ask it. We want to deal with net torque. Unfortunately, there's no pivot point here, or at least no obvious pivot point. Now here's where you guys tend to screw things up a little bit in your notes. And so if you haven't noticed, I've been trying to make a play for you to write some things down that I would normally say and walk past that without thinking about it, then you never remember it again. So if you want to be successful, say on a quiz tomorrow, first 15 minutes of class, you'll note that in this problem, the object's not moving, so there is no pivot point. If it were spinning, there would be an axis of rotation. But this object is not spinning, so there is no pivot point. Torque requires a fulcrum for calculation. So because there is no clear pivot, and since the object isn't moving, both of those conditions have to be true. There's no clear pivot and the object isn't moving. We can choose anywhere to be our pivot. Say that again. Because there is no clear pivot and because the system is not moving and has no axis of rotation, we can pick anywhere we want to be our pivot. Now, there are some choices that will work better than others. We can make choices here to serve our problem if we want. For example, I know all the distances from the end of the ruler to each of the forces, right? We listed them on the board. They're there right now, 20, 30, 50, and 80, right? They're all just sitting right up there. If I chose the location to be the end of the ruler, I already know all my pivot distances or my torque arm distances. I could choose that and I wouldn't have to do any extra work. However, I will point out again, the size of our torque is dependent on R. I can make my problem easier. You see, I can take the pivot and put it wherever I want. Because I can choose anywhere, I could place the pivot somewhere that eliminates one of the torques. That's one less thing I have to calculate. And more importantly, if I put it on one of the unknown torques, I eliminate an unknown, making the math easier. So if you can, this is a hint, colon, space, space. If you can eliminate a torque by the placement of your pivot point, you should do so. Especially if it's an unknown. If you can eliminate a torque by the placement of your pivot, you should do so, especially if it's an unknown. So I'm going to place the pivot point right here, right where the left tension is applied. That's now my pivot point. That eliminates the unknown. Now, there's still 3 other torques. And I wouldn't normally do this in mechanics, but I'm gonna lay out a way for you to do these because I think you guys need a little bit of extra guidance. Do you realize that there are still 3 other torques that we have to deal with? There's the torque from the 500 gram mass. There's the torque from the meter stick's own weight. And there's the torque from the string holding it on the right. Right? 3 forces act on the meter stick. Each one of them can cause a torque. Those are the other 3 torques acting in the system. These torques have to add up to be 0 because our system is in stable equilibrium. And each torque has 3 parts. Setting up a chart. Do you see a chart? Setting up a chart. You should set up a chart. You guys need guidance. This is how I set up the chart for you. I'm listing all the torques vertically, reminding myself they have to sum to be equal to 0. I'm listing them out carefully, and I'm reminding myself that each one of those torques has a torque arm length, a size of a force, and might be subject to the acting of an angle. So now I will go torque by torque, laying out the value of each torque. Also, before I start the problem, like any force problem, a torque problem has torques that can be positive or negative. So, out of the board, is it positive or negative? All right, so out of the board is now positive. We have established that from the beginning. It's like choosing whether up is positive or down is positive. You pick one and you go forward from there. All right, let's start with the 500 gram mass acting as a torque. Right hand rule. Start at the pivot point. I will point in the direction of the torque arm, which goes from the pivot point to the 500 gram mass. I will rotate my wrist until my middle finger points in the direction of the force. My thumb points in the direction of the torque, which is clearly into the board. That must cause a rotation in this direction. Do you believe that if this was the pivot, this force would cause the whole system to pivot this way? So yes, I'm going to say that this is our negative torque because it's into the board. Now look, you don't have to make this hard. Isn't it kind of clear that these things are trying to make the object go that way? And this one over here is trying to make the object go that way? If this whole right-hand rule thing is too much work for you, then you could, because you're the one looking at the problem, say those are clockwise and that one's counterclockwise. I will make clockwise positive and counterclockwise negative. That's just fine. If that's what you wish to do, then by all means do it. I'm showing you how to use the right-hand rule so you are capable of using it. If you don't want to, you can just look at the problem and kind of figure it out. And if you don't like that, you could always put a coordinate system right here and decide whether R is positive or negative based on what direction it goes, and whether F is positive or negative based on which direction it goes. And that would work too. For example, R is positive, but F is negative. That would give us a negative torque. You can do it that way as well. You have options. Everybody understand? Now, I'm going to be a little bit more expedient here. This one's negative, this one's negative, this one's positive. Right, we saw that real quick, and you've all been playing with your right-hand rule. I've been watching you, so you're good. The first torque arm is a distance of 10 centimeters away. I'm going to put everything in meters just to be safe. And the size of that force, 4.9. And I think we can all agree that that's going to be sine of 90 degrees. I'm going to go fast here, because this is the least interesting part. If you don't know what I'm writing down, you should raise your hand and say, Mr. Shelton, stop. But I'm pretty sure the middle of the meter stick is 30 centimeters away from the 20 centimeter mark, right? From 20 to 50 is 30 centimeters. So 0.3 times 0.9 times sine of 90 degrees. Any question where I got any of those? All right, the string is located at the 80 centimeter mark. That is 60 centimeters away from the 20 centimeter mark. So we're looking at 0.6, but we don't know the size of this force. We just called it tension on the right, and it's also sine of 90 degrees. I've laid out all of my torques by doing torque arm length times size of force times the sine of the angle. Any question from where those came from? All right, look, there's only one unknown here. So have at it, right? You can do this. Go for it. You don't need me. Tell me what the size of that tension is. I'll pick on one of you in a minute. I know who I want to pick on. Arseeth, did you figure it out? What's TR? 1.267 newtons. All right, I'm going to put 2.7 newtons. Since you said 0.267, that's a lot of extra numbers. Let's go 1.27. That's great. But of course, that doesn't do as much good unless we get TL as well. Now, we have a way to get TL because we have a relationship from earlier that had both of them in it. We found TR because we found that from torque, but we can now go back and find TL. So do so, please. This is the net force relationship, and that should be enough to let you find TL. How did I get what? I didn't get any of them. But Arseeth got this one. And I'm pretty confident that's right. All righty, so we're all done. Somebody can give me TL. I'm kind of sure I know who I can call in and not get the answer. Olivia, what do you got? I guess she just wants to make sure, huh? All right, 4.5. I'm pretty sure that's okay. Look, the whole thing is going to be 5.8. So 4.5 plus 1.3 is pretty close to 5.8. I think we're all right. Now, so going back to this problem, taking all this away, so now we're talking about taking our object and placing it over here. I'm still looking for this. I want this value for R. What is the maximum value for R that I can put the object there before the system starts to fall apart? TL plus TR still equals 4.9 plus 0.9. And we already know what the threshold is. The threshold occurs when TR goes to 0. That's when the threshold occurs. But at that moment, this just tells me that the left-hand cable holds everything, right? This doesn't tell me where any of these weights can be placed. So if you want to figure out where the weights can be placed, the only place R appears is in our version of torque. So we need to go back to the drawing board for torque and work that out. This one's easier to do if you know what you're doing. If you don't know what you're doing, trouble. So here we go. I will give you some hints. Step 1, decide on a pivot that you will use for this particular problem. You don't have to use the pivot we used before, or you can use the pivot from before, but you need to decide on a pivot. That's step 1. Step 2, lay out the torques acting on your system. Step 3, set those torques equal to 0. Step 4, decide the direction of each of your torques. Step 5, come up with an expression for each torque. So if I do all those things, I'm going to leave my pivot point where it was. I'm identifying the possibility of 3 torques. The torque from the 500 gram mass, the torque from the meter stick, and the torque from the right-hand cable. I've laid all my torques out. I want them to sum to be equal to 0. I'm going to identify the direction of each torque using the right-hand rule or clockwise and counterclockwise. Be careful. When you lay out the direction of your torque, this one's on the other side now. So it's a positive torque, not a negative torque. You guys see that? It's causing a positive rotation. Torque arm length is to the left and the force is down. Lay out an expression for each torque. I don't know where this one goes. That's the whole point of the problem. But I do know the size of the force is still 4.9. Meter stick hasn't changed. It still has its weight at the middle, which is 0.3 meters away from where my pivot point is, and it's still 0.9 newtons. Here's where you have to know something. Here's where you're making a judgment call. We know that we are right up against the threshold when this force, this tension, goes to 0. That's when we're right up against the threshold. That was the whole point. So you have to know that. You have to bring that to the problem. Careful. Well, now I just work it out. Add up all my torques. 4.9 times R minus 0.27 equals 0. That's it. This one's not hard. What does R equal? What's that? 0.06. Is it true?